Hello and welcome to Lecture 7 of the course from Data to Decisions. I'm Chris Mack, the professor for this class, and this is a little different. This is an appendix lecture. It's kind of an optional lecture where I'm going to review a little bit of some simple things related to matrix mathematics. So why should we care about matrices if we're attending a course on statistics and regression, the Data to Decisions class? Well, more than likely, we're going to be using some regression software. We're not going to write everything that we do ourselves as some macro in Excel or write our own code. Instead, we'll probably end up using some commercial software or things like R to do some sophisticated regression analysis. And almost all of these regression programs use matrix methods, as we talked about in the last lecture. Therefore, when you're inputting information into these programs, the interfaces and the discussion about those inputs relate to matrices. When you interpret the results that come out of these software packages, they're almost always described in the context of matrices. So to get a feeling and being comfortable talking about matrices is valuable when using the software. If you go and you grab a advanced regression textbook, something other than an intro to statistics book, chances are very good it's going to talk about matrix math because that's how we solve these regression equations, how we solve the problems to best fit a model to the data. If you go to journal papers in the world of statistics and regression, you'll frequently find matrices discussions. So if you want to understand what they're talking about, you have to have a certain level of familiarity with matrices. Finally, we're going to use the covariance matrix a lot in this class as an example of the kind of output you need in order to properly interpret the results of a regression. So we're going to talk about matrices in this class as well. So let's do a very, very simple and quick refresher course on what a matrix is and how it's described and manipulated. First of all, matrices are rows and columns of numbers. They're generally formatted like this in the square brackets with elements of the matrix given by something like A, I, J. I is the row index, J is the column index. And we say that an m by n matrix has m rows and columns. And m and n could be anything. If the number of columns is 1, call it a vector. We can transpose that vector, and then we have the number of rows being 1. That's a different kind of a vector. We'll talk about transposing in just a moment. This gives rise to an interesting situation. That if I have two matrices of different size, then what I can do with them in relationship to each other is quite limited. For example, two matrices can be equal only if they're the same size. They have the same number of rows and columns. And all the elements are exactly the same. Every element is equal. So Aij is the same for every I and j. So we can only talk about two matrices being equal if they're the same size. Likewise, we can only add two matrices together if they're the same size, same number of rows and the same number of columns. To add two matrices together, we add their elements. If we multiply a matrix by a scalar, that's equivalent to multiplying every element in that matrix by the scalar. The scalar is just a number 5 or 28.6 or something, right? Now things get a little bit more complicated when we try to multiply two matrices together. If I have a matrix A and a matrix B and I want to multiply them together, I can only do that if the number of columns of A equals the number of rows of B. So here I show A is an m by n matrix. All right, so m is the number of rows and n is the number of columns. B is an n by p. You see that the number of columns of A equals the number of rows of B. And when I multiply them together, I'll get an m by p matrix in size. The way we multiply is go along the row of the first one and the column of the second one and multiply the individual elements and add them together. So this A11 multiplied by B11 plus A12 multiplied by B21. So this multiplied by this. And that gives us a first element. When I do this multiplied by this, gives us the second. First row, second column, etc. And we can multiply these two things together. Note that if A times B can be multiplied together, and B times A generally will not be a proper multiplication unless they happen to be square matrices. But even if they are square matrices, matrix multiplication is not commutative. That is, A times B is not the same thing as B times A. Right? If you want to prove that, just pick a pair of 2 by 2 matrices and multiply them one direction, multiply them the other direction, you'll see that they're not the same in general. We frequently talk about the identity matrix. In fact, we talked about the identity matrix in the last lecture. This is a square matrix where all the diagonal elements matrix are 1 and all the off-diagonal elements are 0. We also talk about the transpose of a matrix. In a transpose, we simply swap the rows for the columns. So if I have an m by n matrix, its transpose will be an n by m matrix. And every individual element is swapped. I's and j's become j's and i's of the transposed matrix. The trace of a square matrix is the sum of its diagonal entries, the diagonal elements. And the determinant of a square matrix is frequently used in various contexts. For a 2 by 2 matrix, determinant would be the top left, I'm getting my left-right confused here, top left, bottom right, multiplied, subtracting off the opposite diagonal. So A times D minus B times C. So the determinant is a number. It has something to do with kind of the magnitude, how big it is in terms of the magnitude of the numbers in the matrix. And it's used in a number of contexts. We'll see it in just a moment, how we use the determinant. If we have larger matrices, then the formulas get more complicated, but there's basically techniques of dividing up a larger matrix into a bunch of 2 by 2s and then applying the 2 by 2 determinant. I won't go into the formulas for how to do that, but it's similar kinds of ideas involved. You can go look that up on Wikipedia or other sources of information. We're going to use the determinant in just a moment because it's very important to be able to take the inverse of a square matrix when doing regression. In fact, if we can't take the inverse of a square matrix, then we can't do a regression in the matrix formulation that we've used in the last lecture. We define the inverse of a matrix as any matrix when multiplied by its inverse produces the identity matrix. Right? You can only define an inverse if it is a square matrix. And this is where the determinant comes in. We know inverse of a matrix exists if its determinant is non-zero. If the determinant of a matrix is 0, right, so we come back here, if A times D is equal to B times C, for the case of a 2 by 2, then we know that the inverse doesn't exist. In that case, we say the matrix is singular or degenerate. And that's the case in terms of regression. It means there's no unique solution. There's more than one solution for a best fit set of parameters. So more than one set of parameters will produce the same minimum sum of square errors, for example. That's what happens when an inverse doesn't exist. Some properties of the inverse, if that inverse exists, are shown below. I won't those, but they're there for your reference. The techniques, mathematical techniques for generating an inverse, if the matrix is kind of large, those techniques can be complicated. I won't go into any of the details of various numerical approaches used. I will say this, though. The determinant, if the determinant is 0, then the inverse doesn't exist. The determinant is close to 0. Non-zero, but close. Then we can have problems with the numerical stability of our inverse algorithm. So algorithms that calculate the inverse of a matrix can start to have round-off errors that mess up the stability of the answers that come out if the determinant is really, really small. And so we sometimes have to watch out for that. Technically, an inverse exists, but in reality, it's hard to find it. The determinant is quite small. And the final topic I'll mention, and this will show up, I think, one place in the class. An orthogonal matrix is a square matrix such that when I multiply a matrix by its transpose, I get the identity matrix. Well, that means, since this is the definition of an inverse, this means that for an orthogonal matrix, its transpose equals its inverse. Now, this can only happen if the determinant is either +1 or -1. Now, that doesn't mean that every matrix whose determinant is +1 or -1 is an orthogonal matrix, but you cannot be an orthogonal matrix unless your determinant is either +1 or -1. Some examples and where we find orthogonal matrices to be very, very valuable is when performing things like rotations, reflections, or permutations of the axes and multiplying by a matrix. These kinds of matrices, these orthogonal matrices, are frequently used when manipulating objects in three-dimensional space, for example, in graphics and various other types of things, plus many other uses as well. Well, that's my very brief review of matrix math to give you some ideas of what the terms are that we use and how we use them. I don't have a what have we learned at the end of this lecture because it is simply an appendix for your information. Next time, we'll finish our three-part review of regression. Till then.